So we're going to go over the 5.3 homework. I've uploaded the completed notes, but I wanted to go over the questions as well, so you had some extra help, especially since we didn't get to cover it in class. So it says, give the correct symbol for each of the following sample statistics or population parameter. Sample size, mu is mean, n is sample size, sigma is standard deviation, n is population size, s is sample standard deviation, and x bar is the sample average. Population size is capital N. Sample mean is x bar. Population mean is mu. Sample standard deviation is S. Population standard deviation is sigma. For question 2, it says the larger the sample, the blank accurate the sample mean will be as an estimate of the population mean. So the larger the sample, the more accurate. So the smaller the sample, the more likely we're going to be further from the mean, because we could end up with the largest value and the smallest value. Or the two largest values, or we could end up with the two smallest values, something like that. But the larger we make our sample, the closer we're going to be to our population average, because the closer we are going to be to our actual population. So we're going to be more accurate as our sample size increases. So it says assume that the population of adults has IQ scores with mean of 100 and standard deviation of 15. What percentage of individual adult IQ scores less than 98? So the percentage of individual, so individual is important here. That tells me that I'm working with one person. Adults with IQ scores less than 98 is, so when we're dealing with normally distributed values, we have our formula that we could use, but we use technology for normal CDF. We want a lower bound, an upper bound, a mean, and a standard deviation. Standard deviation is what I always have to be careful of. Do I have one person or do I have a group of people? So this is an individual. So we have one person, so it's going to be the population standard deviation. So less than 98, when it's less than 98, 98 is my upper bound. Negative 999 is my lower bound. So as many nines as I want. The average is 100. The standard deviation is 15. And that is 44. So it's 0.4469. But then it says to round to one decimal place, and it's a percentage. So I'm going to go ahead and multiply that by 100. And I get 44.7%. And then it says the percentage of samples of 36 adults. So this is where our standard deviation is going to change. Our probability, we're still finding the probability of getting less than 98, but now we're talking about samples of 36 adults. So we're pulling every single sample of 36 adults from that population. What's the probability of getting an average of less than 98? What happens is when we're looking at averages, we're reducing the variation because we've taken each of those samples and we found the average of each of those samples. So they're getting closer to the population average. And so then I go second vars, go to normal CDF, and I realize that my standard deviation is going to change. So it's going to be 15 divided by the square root of the sample size. So in this case, it's the square root of 36. And I paste that in, and it's a percentage, so I'm going to multiply that by 100 and then round that to one decimal place. And it's going to be 21.2%. All right, question 4 says, assume that the population of adults has IQ scores with mean of 100 and standard deviation of 15. What percentage of individual adults have IQ scores between 96 and 106? So now we're looking at individual. So this one's going to have the population standard deviation. So we're going to go to our normal CDF, which is going to our density function, which helps us find this probability. So my low bound is 96. Now my high bound is 106. So what's the probability we're going to be between those two values? Our average is going to be the average every single time, no matter what. So when you're trying to find this probability, the average is going to be the average. It's going to be the average. It's the standard deviation that you have to be careful of. am I using the population standard deviation of 15, or am I pulling samples and so that standard deviation is getting smaller? Because it's an individual, we use the population standard deviation, and it's a percentage, so I multiply that by 100, and I get 26.1%. Oh, I typed in 16, not 26, so be careful when you're typing things in. So the percentage of samples of 100 adults. So now we're taking groups of 100. We're finding the average IQ of each of those samples of 100. What's the probability now that the average is going to be between 96 and 106? And when you look at your notes, you'll see that when you find the standard deviation using the standard error formula, that the standard deviation gets smaller. So then the variation in this data set gets smaller. So we're going to look at what happens with this probability here. So now we have 100 individuals in our sample. Now, of course, I could type in 10 there because the square root of 100 is 10, but if we didn't know that, so there is a 99.6% chance that in groups of 100, their mean IQ score is going to be between 96 and 106. So we can see that probability increased significantly because in a sample of 100, it takes that standard deviation of 15 and shrinks it to 1.5. And so we see that. So now instead of being 45 on either side, because that's 3 standard deviations, 15, 30, 45, it's going to be 4.5 away from. So we're looking at a range of 95.5 to 104.5. 99.7% of all those samples are going to be within 3 standard deviations. That's what that is. And then in the population, 3 standard deviations to the left and to the right is going to be 100 minus 45, which is 55, and 100 plus 45, which is 145. So we're looking at a range of 55 to 145. So it makes a significant difference in the spread of our data, and so that's why the probability is so much higher. All right. So it says IQ scores are normally distributed with a mean of 100, standard deviation of 15, complete parts A through D. Sketch the normal distribution of IQ scores and shade the area which represents an IQ of less than 90. So I have this value. That's less than 100. That's more than 90. And that's more than 100. So we're looking at less than 90. It says, what's the probability that one randomly selected person has an IQ less than 90? So probability is going to be normal CDF. Less than 90 means 90 is my upper bound. Population mean of 100. Standard deviation is the population standard deviation. And it's 0.25249. It says the standard deviation of the distribution of sample means. So what is the standard deviation of the distribution of sample means for size 20? So it's one of these two, right? But because we have a sample of size 20, we have to divide it by the square root of the sample size. So then it says, what's the probability that a random sample of 20 adults has a mean IQ score of less than 90? So then we have to adjust this probability for a sample of size 20. So instead of the population standard deviation, we're shrinking the spread of that data. So we divide by the square root of 20. And we get 0.1%, so 0.00143. All right, so here it says, suppose a simple random sample of size n equals 49, so that tells me we have a sample size, so it's not 1, is obtained from a population with an average of 73 and a standard deviation of 14. We have to describe the distribution of the sample means, X bar. So what is this new distribution going to look like? And then find the probability of obtaining a sample of size 49 with an average of more than 75.7, an average of less than or equal to 68.3, and an average of between 70.5 and 77.3. So it says choose the correct description of the shape of the sampling distribution. So the central limit theorem says, and if you look at your notes, it says that the distribution becomes more symmetric as the sample size increases. Our criteria was a sample size of 30. We have a sample of 49, so it's going to be roughly symmetric or approximately normal. So it says find the mean and standard deviation. Well, we just talked about it. The average is going to be the average, so it's still 73. The standard deviation, however, is going to be the standard deviation divided by the square root of the sample size. The square root of 49 is 7, so we'd have 2 there. And so our standard deviation is 2. So now, instead of going from 14 plus 14 plus 14, so if you look at the range of 3 standard deviations, on the low end, we would be looking at 31, and then on the high end, I'm just going to do 14 times 3 instead of 14 plus 14 plus 14 to 115. So in the original data set, assuming it's normally distributed, we would be looking, and we don't know this, but we would be looking at a range of 31 to 115. And again, I don't know that it's normally distributed, but if it was, that's what we would look at. And then in the sample, however, it shrinks the spread of that data because we have 2 times 3 is 6 from 67 to 79. So you can see it's a significantly smaller window that we're looking at. So now we're going to go to normal CDF. We have greater than 75.7. When it's greater than, that's my lower bound, not negative. And then my upper bound is infinity. In theory, right? Practically, it could be something different, but it's not going to make a significant difference when finding the probability. We have 73 as an average, and 2 is our standard deviation. And we have a probability of, it says 4 places, so 0.0885. For less than or equal to 68.3, that is going to be our upper bound. We're still dealing with a sampling distribution, and I can tell that because of the X bar there. Same mean, same standard deviation, or standard error in this case. It's 0.0094. And then now we want to know the probability that it's going to be between 70.5 and 77.3. So again, remember, if an average of 73 with a standard deviation of 2, 99.7% of our values are going to fall between 67 and 79. So 67 to 79, so it's going to be less than 99.7 because it's within that window. And again, that's the empirical rule that I was using there, because we do know the sampling distribution is approximately normal. So the empirical rule would apply there. And it's 0.8786. So almost 88% of the data samples would fall within those averages. Well, it's acting like I didn't answer all the questions, but I did. All right, for number 7, it says large samples of the same size are randomly selected from a very large population that may or may not have a normal distribution. What does the central limit theorem, which is what I was just talking about, tell us about the distribution of the means from those samples? It says simples. The mean of the samples will have a distribution that is exactly the same shape as the population's distribution. Okay, so we're talking about large samples. So the means of the samples will have a distribution that is approximately a normal distribution. Since the population's distribution is not normal, the central limit theorem doesn't tell us anything about that. No. The means of the samples will have a distribution that is approximately the same shape as the population's distribution. So large samples of the same size are randomly selected from a very large population. So what happens is if it's a large sample, and of course, as the sample gets larger, it becomes more and more normal. And so the means of the samples will have a distribution that's approximately normal. That's because it's a large sample. If it was a small sample, then it's going to be approximately the same shape as the population's distribution. Okay, so suppose a simple random sample of size 81, so that's large enough to be approximately normal because it's greater than 30, is obtained from a population with an average of 80 and a standard deviation of 36. Describe the distribution of the sample means X bar. The shape of the distribution is unknown. That is true of the population, but of the sampling distribution, we know it's approximately normal because this is larger than 30. So it says find the mean and the standard deviation. The mean's always really easy to find because it's the same as the average. So if we had a list of data values, we would just find the average there. The standard deviation is going to be 81 divided by the square root of 36. And we can see that that is 13.5. So now we need to find these probabilities. What's the probability that of obtaining a sample with an average of more than 84.4? So more than is my lower bound. My average is 80. My standard deviation is 13.5, or 36 divided by the square root of 81. I did not do that correctly. 36 divided by the square root of 81 is 4. I got my numbers backwards. So then, almost 13.6%. And the 6 after rounds it up to a 7. The spread of this data 3 standard deviations away would be 12 to the left, 12 to the right, because 4 times 3 is 12. So we're looking at 68 to 92. That's going to be 99.7% of our samples are going to fall within that range. Of less than or equal to 72. So that means that is our upper bound. Now, I'm going to find this probability with this value, and then I'm also going to put 0 in there, and we're going to look at the difference. So you can see that, see the effect that that has on that. So here is the probability with the -9s there. And then 0, which is a significant amount smaller than 72, okay? Especially considering the standard deviations for it. Like I said, 68 to 92 is going to be our at 99.7% of all of our samples. So that's why I say 0 is significantly smaller than 80. And if you look, it's the exact same probability. So making this so much smaller in to the accuracy that our calculator gives us didn't make a difference. So then we have 0.02, help if I was typing here, 0.0228. And then between 74.8 and 86.4, 2 standard deviations away is going to be 8 away, so that's going to be 72 to 88. So it's going to be less than 95%, so we can see that. So that kind of, and the reason we kind of think about the empirical rule in that case is because we want to kind of always be checking for errors, right? Because reporting the data incorrectly could affect any kind of conclusion we draw. And depending on what we're doing, it could affect our research. It could cost us money. So we need to think about things like that. The probability here is 0.016, 70 because it rounds up, and making sure we're going to 4 places. Okay, and I'm going to double check that. So 74.8 to 86.4 with an average of 80 and a standard deviation of that. And I had the 0.02. So I saw a 1.7% probability, and I knew I needed to check it because I knew it should be closer to 95 because it was close to 2 standard deviations away from the mean. So be careful, because if you already have something in your calculator, it could, and it will obviously, affect the probability that you get. So again, checking for errors is important. And that is how we're finding that probability. Continue. All right, so determine whether the statement makes sense is clearly true or doesn't make sense is clearly false. Explain. A process consists of repeating this operation. Randomly select 2 values from a normally distributed population and then find the mean of the 2 values. The sample means will be normally distributed even though each sample has only 2 values. The reason this is true, because that's way less than 30, is because the population is normally distributed. So the statement does make sense. The central limit theorem, it's not the central limit theorem. The central limit theorem is when you don't know the shape of the population or it's not normally distributed. So it makes sense since the population is normally distributed. The distribution of the sample means will also be normally distributed regardless of sample size. Suppose a geyser has a mean time between eruptions of 71 minutes. The interval of time between the eruptions is normally distributed, so that's important because it doesn't matter about our sample size, with standard deviation of 23 minutes. Answer the following question. What is the probability that a randomly selected A, 1, so we're using the population standard deviation, that a randomly selected time interval between eruptions is longer than 82 minutes? So probability is longer than 82 minutes. Our average is 71 minutes and our standard deviation is 23. So we have, says 4 decimal places, so 0.3162 or 31.6% of those eruptions. The proportion of them that are longer than 82 is that. What's the probability that a random sample of 9 time intervals, so the number 9 would give me pause, and I'd be like, okay, that's not 30, but then I would go back and see that it is normally distributed, so it's okay, is more than 82. The 9 affects the standard deviation, so it affects the spread of the data. So we're going to do 23 divided by the square root of 9. If you know that's 3, just type in 3. And 7.6% of those are going to be, those samples are going to have an average that's longer than 82 minutes. What's the probability that a random sample of 19 time intervals has an average of more than that? So that affects our standard deviation. It's shrinking that standard deviation even more because we're increasing our sample size. So now we're down to 1.85% of samples of size 19 should have an average of more than 82 minutes. On average, it should be that. What effect does increasing the sample size have on the probability? Provide an explanation for this result. So the probability increases. That's not true. It decreased. So the probability decreases because the variability in the sample mean increases. Variability is decreasing. So the probability decreased because the width of the interval got smaller and smaller as we increased the sample size. IQ scores, so we're back to IQ scores are normally distributed. Now we have a mean of 95 and a standard deviation of 18. Assume that many samples of size n, this is important because that's the central limit theorem, even though it's normally distributed. So when it's many samples, we are guaranteed that regardless of the shape of the parent distribution or the population distribution of size n are taken from a large population of people, and the mean IQ score is computed for each sample. If the sample size is 81, find the mean and standard deviation of the distribution of sample means. So the average is going to approach the population average. The standard deviation is going to, it says round to the nearest tenth, is going to be 18 divided by the square root of 81. 18 divided by 9 is 2. If the sample size is 169, find the mean and the standard deviation. So the mean is still 95, and then the standard deviation then becomes 18 divided by 13, or 18 divided by the square root of 169. Oh, I had an extra parenthesis there. 1.4. So we can see it got smaller, so the spread got smaller. It says, why is the standard deviation in part A different from the standard deviation in part B? Choose the correct answer below. With larger sample sizes, as in part B, the mean tends to be further apart. That's not true. The means do not tend to be further apart. They tend to be closer together. So means tend to be closer together, so they have less variation, which results in a smaller standard deviation. Okay, that same sounds correctly, but I'm still going to read all the choices just to make sure I didn't misread something. With smaller sample sizes, as in part A, the means tend to be closer together. That's not true. With smaller sample sizes, and we have larger sample sizes, so it's going to be this. All right, for question 12, the last question here, the shape of the distribution of the time required to get an oil change at a 20-minute oil change facility is unknown. So we have to be careful of our sample size because we don't know the shape of the population distribution. However, records indicate that the mean time is 21.4 minutes and the standard deviation is 3.1 minutes. Complete parts A through C below. To compute probabilities regarding the sample mean using the normal model, what sample size would be required? Needs to be greater than 30. What's the probability that a random sample of size 40 oil changes results in a sample mean time of less than 20 minutes? So we're looking at less than 20. So that means 20 is my highest that it can be. The average is 21.4 minutes. And then if I forget to edit my standard deviation, I'm going to get 32.58%. However, once I adjust for, well, if it can click the buttons here, for the sample size of 40, again, we divide by the square root of the sample size, we get 0.2% of samples are going to have an average time of less than 20 minutes. So if my business that I've franchised or are reporting in a day that their average time and they're servicing 40 cars is less than 20 and the average is 21.4 with that standard deviation, I'm going to be a little leery because that would be really unusual to have an average of less than 20. So I'm going to do more research into that. If they have an average time of less than 20, great. But I'm still going to double check. Suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 and 12. Treating this as a random sample, at what mean oil change time would there be a 10% chance of being at or below? 10% is an area. So when we need a value, we have to go to the inverse of normal CDF. So now we have the probability. Your calculator will not have this tail portion. Yours defaults to left. Luckily, this is at or below, so it's automatically in the left tail. We have an average of 21.4. The biggest mistake that students make is because this 40 oil changes is kind of like, it's almost like it's hidden in the problem and it's hard to see. But it does count as a sample size. So we have to divide by the square root of 40. Of course, your calculator won't have that. Some of yours will. And so it will be in the left tail. For those of you who don't have that, it defaults to the left tail. So it's on the left side of 10%, which is what we want. And that's going to be, it says round to one decimal place, below 20.8 minutes. Okay, so if you have any other questions about 5.3, please reach out to me and I will be happy to help. See you on Monday.